To study group action, you need a group G and non-empty set capital A. And a group action is defined by this law. You can see that this red dot, G dot A. It means that G is acting on A. A few textbooks says that G is acting on A from the left because G is present on the left hand side. And similarly, they define the right action. This is very similar to defining a left coset or a right coset, right? But rather than following the terminology of left and right, we just define the group action straight away, right? This is G dot A. And this group action, it means that every element of group G will be acting on every element of set A by this rule, right? And there were two postulates also. First postulate was for any two elements of capital G, G1 and G2, and for any element of capital A, that is little a, this property must hold, right? It means that when G2, this is the result of action of G2 on A, and of course this will be a member of capital A, because you know that whenever an element of group G acts on element of set capital A, the result lies inside the set capital A itself, right? So that's why I'm saying that this element is a member of capital A, and since it is a member of capital A, so another member of capital G, that is G1, I can act on it like this. G1 acting on this result of the action of G2 and A, and that the final result, of course, this result whole value should belong to set capital A itself, right? So this should be equal to the action of the element G1 G2 of G on the element little a of capital A, right? Please note that the right hand side is the result of a single action of the element G1 G2 on element A, but the left hand side is the result of simultaneous actions of G2 on A and then G1 acting on the G2 output of A. And the postulate says that should be same, or you can say that the result of these two actions should be so this same. Is the pictorial representation of this equation, right? You can see that this is a blue yellow patch. The yellow patch corresponds to the left hand side, G1 acting on the result of action of G2 on A, and this blue patch is the result of action of G1 G2 on the element A, and this is of course the right hand side, and this yellow patch is for the left hand side. The postulate is asking you get these patches equal in value, right? It means that the number which will be here in this yellow patch should be equal to the number in this blue patch, and those, of course, those numbers should belong to this set capital A. This was the first postulate, and the second postulate is quite easy. It says that for the identity element, identity element is denoted by the letter for group G, and for all values belonging to capital A, this postulate must hold. And this should be read like this: E acting on A must give A. It is not E multiplied with A, right? It is E acting on element A should be equal to A, and this must hold for every value of little a belonging to capital A, right? And if you see the composition table of group action, it does mean that the top row, this is for capital A. The elements of capital A are listed here in the sequence. That should be identical to this first row. Since first row corresponds to the identity of group G, here you write the elements of group G, and here you write the elements of set A in the sequence. And then the results here, like this result, this number is just the result of the action of E on A, right? So this E will be acting on each member of this capital A, right? And hence this first row should be identical to the top row, right? So this is what the second postulate is asking you. And this is a group action of group G on set A, and when you have a group action, then you have permutation there. And how does a permutation comes into existence? by the action of group G on set A. So whenever you study a group action on set A, there must be some permutation, or you call it permutation representation. We'll do this. Fact 2 is actually representing the correspondence between the group action on set A and the homomorphism from G to SA, right? So these are just correlated to each other and can be taken as two sides of a single coin. If one will happen, then other will happen automatically, right? Okay. So the fact one was for every element little g of group G, right? Sigma G is a permutation of A, and this is very important. At this step, you just come to know that of course there exist permutations, which represents this scenario. I mean, an element of group G is acting on the elements of set A. Process or this phenomenon can be represented by a two-line representation called a permutation, right? So this is visible from here. Where is that? Where is that? This one, yeah, this one. You can see that this picture. You see this picture. This was the original sequence of the elements of A1, A2, A3, dash, 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 AJ, right? And when this element G, little g of group G, elements of acted on A, this, then when G acted on little a1, it gives little b1. When G acted on little a2, it gives little b2, and so on, right? Of course, each entry here must be a member of capital A, right? So we can say that this sequence B1, B2, B3 up to Bj must be some rearrangement of the original sequence of the elements of capital A. I mean, these elements are not the new elements actually, though I have represented them by B1, B2, B3, and so on. Actually, B1 may be equal to A5, B2 may be equal to A3, B3 may be equal to A7, and so on. Right? So that's a fact what is represented by this these two lines, right? See this. This is the original sequence A1, A2, A up to AJ. And these are the images B1, B2 up to Bj, but B1 is nothing but the action of G on A1. B2 is nothing but the result of action of G on A2, and so on. And of course, this two-line representation, I mean, these are the actual and these are the images after action of G and on capital A by a single element G. Of course, this is not the result of the whole actions, all of the actions. It just represents one action, right? Action of G on all the elements of A, and there will be more permutations like this. Of course, the second line will be having a different arrangement of the initial line, right? Okay, so this is indeed a permutation, and this fact which you can see here in this picture, that can be proved mathematically, right? And this is the fact number one, that for each element of group G, sigma G is a permutation of capital A, right? It means that every element of group G, which is like a predator, is actually a permutation, right? You are representing a predator by a permutation, because what a predator is doing here, a predator is an element of capital G, is just disturbing the sequence of elements of capital A, right? That's why they are called disturbing elements, or and disturbing elements are of course denoted by a permutation, right? Permutation is nothing but a rearrangement or shuffling or disturbance, one of the disturbance, right? Okay. The proof goes like this. If you want to prove that sigma G is a permutation on set A, you need to prove that it's a bijection, because a permutation is nothing but it's a 1-1 on 2 function from set A. If you want to show that it's a bijection, you need to show that it possesses a two-sided inverse, right? If a function has a two-sided inverse, then of course it's 1-1 on. The first board goes like this. You started with sigma G, O sigma G inverse A, and O is the operation. Please note that this O is the operation. This indicates for the permutation composition. You know that between two permutations, use this symbol generally and the letter small o. Right? And of course, these are the members of symmetric group of symbols of A. That's capital S subscript capital A. Right? Although we have not mentioned that set here yet, okay, you can see that here you cannot see capital S to the subscript capital A because that is mentioned actually here only, right? The first part, in the first fact, we haven't used that these are the members of SA. Though you know that the permutations are the members of set capital SA, right? And if you want to prove this, then you want to use the property of function composition, like f o g of x is actually f of gx, and then sigma g inverse A should be equal to g inverse dot A, as you can see it here. I will write it here too. This can be written as or sigma g A equal to g dot A, right? And dot means action actually. This is used proving this fact number 1. You can see here, okay? And then this is sigma g of g inverse A, again using this boxed law. It should be G acting on this. Now you can use the postulate number 1 of group action, since you are saying that this is a group action, so we can freely use that postulate 1, and that gives you GG inverse dot A by the property 1 of group action. And GG inverse being a member of capital G, that should be equal to the identity element of G and E dot A. And now immediately comes the postulate 2 of group action. Please note that this is not, this A is not due to the multiplication of A with E. This dot doesn't mean multiplication. It means E on A, and that gives you that. And this sigma G inverse is the right inverse of sigma G. Right? Similarly, you can prove this. Okay, from the right hand side, you can also get this A. It means that it possesses right inverse. Okay. So the fact 1 is proved. Now we are coming to fact number 2, and this is just like going to the second side of a coin. Now you are going to the other side, the talking about homomorphism phi, the function which actually relates the elements of group G to the elements of SA, and this is indeed a permutation group, right? Symmetric group, you call it symmetric group. Okay, so the proof goes like this. The map phi map is from group G to the symmetric group capital A phi, and such that this map is from group G. So the element of this G will be little g, right? And the image must lie in this, and that should be equal to sigma G, as you just mentioned here that sigma G is a permutation of capital A, so it should be a member of SA, right? Because all the permutations of capital A are in set SA, right? So this is how the homomorphism, and you have to prove that this is a homomorphism. We have not proved that it is a homomorphism. It is just a function, right? Phi G is equal to sigma G, and for all values of G belonging to G, right? Okay, you want to prove that this is satisfies the homomorphism property, and that is phi. If you remember the homomorphism property, there is phi G1 G2, and since these are the members of group G, and group G, the operation of group G can be any operation. It may be plus, multiplication, addition, modulo, any operation, right? So I'm not using any symbol here between these G1 and G2, is equal to phi of G1, and of course this will be a member of SA, and SA is a symmetric group. The operation is this composition, right? And phi of G2, phi G2, right? For all values of G1 comma G2 belonging to G, you need to prove this this property, and this is a property of homomorphism, right? Okay, so to start the proof, we should pick the left hand side, right? LHS, and that is phi G1 G2, and since phi of G is defined this way, so you can write it as sigma G1 G2. But in order to prove this, why don't you put here A, because this is what is this? This is a permutation actually, and permutation will act on an element and a member of capital A. So that's why you should write it as capital A. This is more precise actually. There's no point to write FOG equal to FOG. FX is there. I mean, there should be some entry, right, on which this this is acting. Okay. Now, following this is sigma of G1 G2 of A, and that must be equal to, if you follow this definition, what is that? If you follow this boxed definition, then you will see that that should be equal to G1 G2 acting on A, right? So I am using the above definition also, G1 G2 acting on A, and I should write it as like this, G1 G2. You should try to prove the right hand side, okay? And this is your right hand side. RHS. The right hand side is phi of G1 O phi of G2, and since these are functions actually, phi G1 is a function, phi G is a function, so we should write an element little a here, which is a element of capital A. They must be acting on capital A. Okay, now using the I should use the fact that why I have done this. Let me write it using I used here phi G equal to sigma G. This was the definition, and using how this came sigma GA equal to G acting on A, right? So two simultaneous definitions were used here. Similarly, this can be written as phi G1 or phi G2A, and if I write it like this, this is just function composition phi G1 and G2A phi will be sigma G2A, right? And this is the definition I used here, this one. And if now you use phi of phi G2 of this, and we should use function composition actually, phi G1 and sigma G2A, right? Now this should be equal to, as per that definition, that should be equal to sigma G2, that should be G2A. Okay, fine, that should be G2 acting on A, right? And I should write it here only. Okay, no problem, G2A, fine. And this is phi of G1, right? And phi of G1 should be sigma G1. This is sigma G1. Now it's clear, right? Okay, and then it must give you what? It must give you G1 acting on the action of G2 on A, and by the property, by the postulate, first postulate of group action, you can always write this as G1 G2 acting on A. So I will write it here by property 1 of group action, right? Okay, so now you can see that left hand side is actually equal to the right hand side, so that's the complete proof of this fact. Important thing about this phi, because phi just came into existence now. Phi is homomorphism, and this should be written in a red color, because red color is remembered for a long time, right? Red color is visible from a long distance actually. The homomorphism from, and why shouldn't I name it phi? Homomorphism phi from G to SA is called the permutation representation of the given group action, right? And what was group action? Please do not forget that this capital F, this was the group action, right? Left was the group action, and it is associated to this permutation representation, capital phi, right? Okay. And if you want to draw a picture for this, because that will be good for you if you want to remember the actions of group G on set A. Actions of group G, right, on set A is I should make like this arrow, like this one, and back arrow, this one. Both are reversible phenomenon. You can jump from one to another very easily, right? And that is morphisms, or you call them permutation representation also. Morphisms from group G into symmetric group SA, right? So this is what the whole scenario means, and this is just by a single line. You should remember this thing, and that all the actions of group G on set A are in 1-1. This is called 1-1 correspondence, means there is bijection, right? Are in 1-1 correspondence to the homomorphism, all the homomorphisms from group G into the into. Please note that is the word into. It's not onto. It doesn't mean that this mapping is onto. This mapping is actually into. This mapping, this one, where is that? This mapping. It doesn't mean that it is onto. It may be into, right? Because if capital A, set capital A has 3 elements. I'm asking this question to all of you. Suppose capital A, the set A, has 3 elements, right? And capital G has 4 elements. Group actions will be there. My question goes to Ms. Priyanka.
Yes, sir.
How many group actions will be there? How many rows will be there if you construct the composition table of this group action? I'm repeating my question. Capital G has 4 elements, right? So if you imagine the composition table of group G, the left hand this one, where is that? Yeah, this one. This will be having 4 elements, right? And set A has 3 elements, so this top row will be having 3 elements, right? How many permutations will be there? I'm asking you the number of permutations.
3.
Number of how many elements did G had?
So 4.
4. How many rows will be there in this? How many rows? 3 or 4? How many rows will be there? 4 rows, no?
Yes, sir.
So there will be 4 permutations, right or wrong? Because the permutation is constructed like this, no? Just pick the top row and you just pick the resulting row. Since you are saying that there are only 4 rows, since there are 4 elements in G, so there will be 4 permutations. Yes or no? Am I right to say this? Okay, so you are saying that there will be 4 group actions, or you can say that. Or yes, yes, there will be 4 group actions. There will be 4 rows. Okay. Okay, so there will be 4 permutations. Please keep it simple. 4 permutations, right? How many permutations does this set has? How many permutations? Can you tell the cardinality of this essay, Priyanka? A was having 3 elements. Hmm.
Sir, 6.
3 factorial equal to 6. But the permutations corresponding to the group actions were only 4. You just told me, right? So what does it mean? Is it onto map or into map?
Sir, onto.
Oh, why you are saying onto? Priyanka, SA is having 6 elements actually. You just told me because A was having 3 elements. Into, yeah. The image of G is having only 4 elements. You just told me. And you just told me that SA is having 3 factorial equal to 6 elements. So what about those 2 elements? They were not mapped to any element of G. Are you getting my point? Let us go back to the example we discussed yesterday, and which Mr. Mridul was unable to understand. I give the example of your class BSc 5th semester, right? You are 3 students. And the university allotted you the sequence, this sequence. Roll number 1 is, I think, Mr. Mridul. Roll number 2 is, I think, Shreya, and roll number 3 is Priyanka. I know that this is the sequence of your roll numbers, right? MSP. This is the original sequence of your set. This is your set A, capital A. So this is the original sequence of the elements of set A, right? And there is a group of faculties, mathematics faculties, which teach you in every semester. And if you consider the example of this semester only, this is your 5th semester, a few faculties are teaching you, including me, right? And whenever this is N means me, right? And this is other faculty X, this is another faculty Y, this is another faculty Z, right? You have 4 faculties which are teaching you, and whenever they teach you, or whenever they enter in your classroom, there is a shuffling of your the sequence actually. And what does it mean actually, shuffling? It doesn't mean that your roll numbers change. It means that their sequence of seating gets changed, right? Sometimes Mridul sits in first place, Shreya in second, and Priyanka in third, which is the actual sequence. And sometimes due to the entrance of a faculty, this faculty, the sequence gets changed. Some Shreya sits at the first position, then Mridul at second, and Priyanka at third. Is possible, right? So it means that when n is the element of group G, the element of group G is acting on this set, and the sequence gets disturbed. That becomes SMP. So due to the action of this faculty, this is n. I should write it as sigma n, because this was due to this faculty n. So I should write it as sigma n is just this permutation. The original sequence was MSP as given by university, and the disturbed sequence due to the action of n on your class is SMP, right? So this is the action of element n. Similarly, there will be some action by faculty X, and your original sequence was MSP, and when X entered into your class, your sequence got disturbed. Maybe Priyanka gets the first position, right? And then Mridul here and Shreya here, right? So I'm asking you that how many actions are possible. This is the first permutation. This is second. Similarly, there will be sigma y, and similarly there will be sigma z. They are actually 4 permutations. You know that these are 4 numbers, right? 4 permutations, but the actual arrangements of these 3 elements were 6, because you know that if there are 3 persons, then they can be arranged in a queue in 3 factorial ways, that is 6. So the actual arrangement, the total number of arrangements, possible arrangements, were 6, right? But the permutations, which were, these are the permutations which are just due to the result of action of the elements of G on the elements of A. Those are actually 4 in number, right? What happened to the rest of the 2 permutations? None of the member of group G was able to act on A to give those rest 2 permutations. That's why I'm calling this an into function. It's not onto, so that's why this word is written here, into. And this ends that what should I say, that confusion which Mridul was having yesterday. The example, what I'm trying to say that, I mean, how this is related to the real life scenario, this group action. Now, Mr. Mridul,
Yes, sir.
clear to you?
Yes, sir. काफी clear है अभी तो.
राइट, ठीक है. तो ये भी क्लियर हो गया होगा कि क्यों जी के मैम, जो जी है, लिटिल जी मतलब की फैकल्टी, राइट, क्यों उसको देखा जा रहा है परम्यूटेशन की तरह. कहीं आप कल से ये ना कहने लगे कि जब आपकी ग्रुप थ्योरी की क्लास होने वाली हो कि परम्यूटेशन इज जस्ट गोइंग टू टीच नाउ. हो सकता है आप ये भी कह दें, क्योंकि यू आर टेकिंग, आपको एक नया डायमेंशन खुल गया है. आप किसी एलिमेंट को, ग्रुप के एलिमेंट को, यू आर टेकिंग हिम और हर एज अ परम्यूटेशन एक्चुअली. तो इट इज पॉसिबल दैट इन द नेक्स्ट upcoming classes, you will tell to your colleague that a permutation is coming to teach us, right? Okay, this is what a group action means, and there is always a bijective map, right, between the actions of group G on Saturday. All the actions, you can see that there are 4 actions. I just rubbed that, right, and to the homomorphisms of G into symmetric group SA. Those permutations are not just ordinary permutations, those are actually homomorphisms, right? And those were homomorphisms just because of those 2 postulates. Please notice that. A permutation is not homomorphism every time, right? But in this scenario, a permutation is behaving like a homomorphism. Or you can say that a permutation is satisfying the homomorphism property in addition. And that was just possible due to the 2 postulates of group action. You're getting my point? This is a remark, very important. And now we should proceed further. We should proceed further to define few more terms like a faithful action. And what is a faithful action? I should write that. I should make a remark of this point, and why don't I write it another remark, because that is just a small point. This is a remark number 1 actually, 1, and this is remark number 2, right here. Not the action of group G on set A is faithful if a distinct elements of group G induce different permutations, or you can call them homomorphisms also, no problem, because every permutation is a homomorphism in this scenario only, It's not true that every permutation is a homomorphism. No, right? Induce the different permutations in what? In where do permutations live? Priyanka? Where do permutations live? What is it set? SA, right? So this is the definition of faithful. Okay, and if this is not true, then it's called unfaithful. That's clear. I will write to the third point, and these are just a small definitions, so I'm making them as a remark only, right? The third is called trivial action, right? Trivial action, and the action defined by like this G dot A. It means that G element G is acting on A, and if it is equal to A again, it is possible that I rubbed that actually. It is possible that for some element little g of capital G, there is no disturbance at all, right? Okay, so if it happens, then that action is called trivial action. And if it happens for all of G, not just for single G, because there will be of course single G, and that is equal to identity element, and E dot A equal to A is always true. I mean, if the identity element act on the set A, then the result is the same. There's no disturbance in the sequence, right? But few actions are there that all the elements of group G are not disturbing the position of any element of little a, right? And then that action is called trivial action, defined by G for all G belonging to G and for all A belonging to A. If this happens, then is called trivial action. Trivial action. Or you say that G acting on A trivially, call it like this too, right? You're getting my point. Priyanka, Radul, is it clear to all of you?
Yes, sir.
Radul?
Yes, sir.
Okay, fine. Then it's called trivial action. And what should I prove now? Trivial action. Okay, that's fine. And how does trivial action? What does a trivial action look like? I should copy the composition table. This composition table actually, and I will show you this one actually. Yeah, this one, and I will show you how it looks in the form of composition table. If you want to visualize this trivial action, right? Okay, so let me paste it here. This one. Okay, so this is trivial action. You can see that the top row is for the elements of capital A, and now this left hand side column is for the elements of capital G, right? And yeah. Fine. Yeah. So this should be actually here we have element A actually, right? A, and this this was the column corresponding to capital A, little a, sorry, right? And you can see that the first element is the identity element, and the row corresponding to the this small e is just identical to the top row, right? And if it is true for all elements, if I make a few more elements here, let me make here G2, and here I make G3, 1, and I make few rows here like this, and this is also A, and this is also capital A. Okay, and here I write capital A again. This is the same as the top border row, capital A, and this is also same as the top border row, right? So this situation here, every row is identical to the top border row. You can see that each of these rows each row is identical to the top row, right? And yeah, you can see that, right? Each of these rows are same as the first row. This is called the trivial action. This picture represents a trivial action. Trivial action of group G on set capital A, right? Is it clear to all of you? Trivial action, right? And what about this faithful? Where do I write faithful? Yeah, faithful. How does the composition table for a faithful group action look like? Radul, can you tell me? What will happen in the faithful group action? The composition table of that. I should just paste it here actually. Let me make another table. Okay. Yeah. No. For faithful action, each row should be distinct. This is some other sequence of write it as this is G1, this is G2, right? And each of these rows must be distinct, right? I can write the elements like B1, B2, dash 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 dash, and the sequence is let it be Bj, and this is sequence C1, C2, dash dash Cj. So what it indicates that each of the rows are distinct this time, right? Each row is distinct, right? And then you call it faithful action. Faithful action. Try to remember these pictures actually, because pictures tell a lot and they are remembered for a long time, right? So all rows are distinct in the composition table of group action, and you call it faithful action. And if all rows are same, then you call it trivial action, right? Now I think it should be clear to all of you, right? The topic is group action, and again I'm saying that this is very important and a completely different perspective to view groups actually, right? And this will be carried for the next lectures also, because Since now onwards, we'll be talking about groups and subgroups related to group action, not just due to the properties we studied earlier in group theory 1, right? So everything now here will be considered as an action. Even you studied cosets also. Cosets were also a kind of group action, because to form a coset, you need a group G and you need a subgroup capital H. In that case, that is not a simple set. H is not a simple set. H is a subgroup actually. That is, and then you pick up the element little g from group G, and then you operate it with capital H. That gives you coset GH. You remember that? That is actually group action. It's again a group action, right? So everything you studied so far can be viewed in another sense of group action. Okay. This is it for this lecture. Tomorrow we will definitely study a few more things, right, about group action. Okay.